So there are many different ways we can write vectors. We're only going to talk about and look at 3 of them. First way is component form, let's say we have some vector v, and it's got certain values. Let's say it has a certain value in the x direction, a certain value in the y direction, and a certain value in the z direction. So this would be a 3-dimensional vector. We can write it in component form as a matrix. So we'd have some value in the x direction, some value in the y direction, some value in the z direction. And this is a component form in a column view. We can also have the same component but in a row view. So we do a row matrix. So essentially a 1 by 3 instead of a 3 by 1. And it means the exact same thing. So it's just kind of preferential based on how we write these, or if we need to do matrix multiplication, if we need to like multiply 2 vectors together. But this is essentially what we're going to come up with here. And now I could give these actual numbers, like let's say I have a vector where I have 1 in the x direction, 2 in the y direction, and 3 in the z direction. I could write that in this component form, just like this. 1, 2, 3, where I don't have to include the x, the y, and the z, because that first spot in my matrix always is the x directional spot. The second spot is always the y directional spot, and the third spot is always the z directional spot. So those are already predetermined and assigned. Now let's look at writing that same vector, but in unit vector notation. So we can say we have that same vector v, and instead of writing it in a matrix form, we're going to write it as some value in the x direction. We're going to denote that it's the x direction by using the letter I and doing this little funny hat above it. So it's called I hat. And then I'm going to add to that whatever variable I have that's going in the y, or whatever number I have that's going in the y direction. And I'm going to denote the y direction by j hat. Then I'm going to add whatever number I have going in the z direction, and I'm going to denote that by the variable k hat. And this is how we would write it in unit vector notation. I can use those same numbers. So let's say I still have that same vector where I have 1 in the x direction, 2 in the y direction, and 3 in the z direction. I would write that, and it would just look like this. 1 I hat plus 2 j hat plus 3 k hat. And these are the same vector, just a different way to write it. Now the other direction, or the other form in which I can write a vector, is called polar coordinates. Polar coordinates has to deal with the magnitude of the vector and the angular direction in which it is going. And we can do that in 2 ways. So one way is where we see that same vector v, and instead of writing x, y, and z, we write some r as denoting some r for radius, or you can think of this in the same terms of as a hypotenuse, because that's kind of what it correlates to if you're thinking of trigonometry. But we represent it with the letter r, and we have a comma behind it, and we use the Greek letter theta to denote some angular displacement. So the r is the magnitude of whatever the vector is. It's the complete length of that vector. And then the theta denotes its position around a unit circle. Another way you can see this written is that we have some vector v, and it's r in magnitude, and we give it coordinates in terms of north, south, east, and west. And I'll show you how that's to be done, but we also have to give it in association in terms of angle. But all this coordination does is break down our unit circle into its corresponding coordinate system. So like either the first coordinate system, the second, the third, or the fourth. All it does is it breaks that down for us, so we don't have to say 270 degrees, right? We can always keep it in terms of 0 to 90 degrees, which is a little bit easier for our brains to think about. So to better understand our vector forms, we're going to look at an example problem. So let's say you have a friend who is obsessed with physics. They want to conduct an experiment. While you're standing still, your friend decides to walk away from you by 4 meters, and in the direction of what we would call 25 degrees north of east. So what that direction means is that if I look at the east direction, which on a xy axis is directly in the positive x direction, I am going to go towards the north direction, which is a counterclockwise motion, and I'm going to go that direction by 25 degrees. So it tells me that this angle here is 25 degrees. This also tells me that the magnitude of this vector, or this motion, is 4 meters. Then your friend stops, they turn, and then they walk 5 meters at 70 degrees north of west. So the way I would determine this direction is the direct west direction on an xy coordinate system is in the negative x direction. So that's due west. I'm going to be going towards the north direction, which in this case is clockwise motion, and I'm going to go that far by 70 degrees. So this angle right here is 70 degrees. And the magnitude of that vector, or the distance that they walked, is 5 meters. So I'm going to write these both in the component form, the vector notation, the unit vector notation form, and the polar form. I'm going to start by writing this in the polar form. And then we're going to use what we know about trigonometry to write the component form and the unit vector form. So the polar coordinate form is going to look something like this. For vector A, and I always denote that it is a vector by the little arrow above it, because vectors have both magnitude and direction. So it cannot just have a number associated with it, it has to have a number with a direction. And that is going to be equal to the 4 meters, and I'm going to write it in this way. It's at, so comma, I can either write it the exact way that they have it in the problem, or I can use it on terms of an overall circle at, so 25 degrees, and I'm just going to use the first letters for abbreviation here, north of east, and that's a perfectly acceptable polar coordinate form. I could, however, also write it in terms of a unit circle, so I can say that vector A is equal to 4 meters, and it's, in this case, if I think about where my unit circle starts, it's a really bad drawing of it, but this is 0 degrees, this is 180 degrees, and I always go counterclockwise on a unit circle. So I start this way, so it would just be 25 degrees. So both are acceptable forms in polar coordinates for our first vector. For vector B, the way I can write this as, so the magnitude, which is the 5 meters, and then I can either write it as 70 degrees north of west, or if I wanted to write it in terms of a unit circle. I'd have to actually do a little bit of deductive reasoning or adding on to it. But essentially, the magnitude will stay the same, so this is still 5 meters. But I can't just write 70 degrees anymore if I'm putting it in terms of a unit circle. So I want to think about where that 70 degrees is on the unit circle. This is where my vector is. This is 70 degrees. This is 180 degrees, and this is 0. So I can look at in terms of a unit circle, the vector I actually want to write is this vector, the angle I want to write is this angle right here. This is the angle theta that I want to write. So the way I would determine that is just take 180 minus 70, which gets me 110 degrees. And that's the angle I would put here if I didn't include any geographical directions. Now, keeping everything in polar coordinate form doesn't actually really help us when it comes to adding vectors together. What I actually want to do is I want to convert it either to the component form, or oftentimes what we'll use is the unit vector notation. Because when it is in one of those forms, I can directly add the components of either the matrices or the unit vector notation. And how we do this is we basically use our knowledge of trig. We break both the vectors into mini right triangles. So the first vector, vector A, becomes its own little unique right triangle, where this is 4 meters, and this is 25 degrees. And this is my y value if I line it up on my xy axis, right? Because this is in the vertical direction, that's my y direction. And then my horizontal direction, that's my x value. And I can kind of use this along with its placement to deduce what are the values of those sides. So sine of that 25 degree angle is going to be equal to that y value over my 4 meters. And I can just rearrange this using algebra to solve for y. So y is equal to the 4 meters multiplied by the sine of 25. I will say an important note here. When you plug it into your calculator, make sure that if I'm using 25 degrees, that's a degree, not a radian. Your calculator's mode is in degrees, not radians. Otherwise, you're going to get a completely different number. But we should get something like y is equal to 1.690473. And it's okay to round to two significant figures for this problem. Most of the time, us physicists, we're not super picky with significant figures. So this means that my y value, this value right here, is 1.69 meters in length. Now, what does that tell me about this position right here? That tells me that, so this is my starting value at right down here, this is y equals 0. This tells me that this y value up here is at 1.69 meters, because that's the difference between the two. And subsequently, I can use cosine of the 25 degrees, which is the adjacent over the hypotenuse, so in this case, the x value over that 4 meters, rearranging it to solve for x, and find out what that x distance is. I get something like 3.6. We'll round to the nearest or the second decimal and get 3.63. And that tells me that this distance, so this length here, is 3.63 meters in length. Since this is at x equals 0, this has got to be at x equals 3.63. So that gives me both of my components for this vector. This is a two-dimensional vector, so the vector component form, or the matrix form, for A can be written, if I use the column matrix, my x value becomes 3.63, and my y value becomes 1.69. And that is how I can write this in the component form. Subsequently, I can write it in the unit vector notation as 3.63 I hat, that's the x direction, plus 1.69 j hat, that's the y direction. And that gives me the direction of both of those. Now, it is important to note that both our a values are in their positive directions. I'm going in the positive x direction and the positive y direction. There's a few different ways we can account for that with other vectors, so it's going to become important for vector b, and we can account for it in a few different ways. We can either just kind of naturally deduce it, or we can use a different angle, and I'll show you both methods. All right, so now let's get down our vector b in component and unit vector notation by making the second right triangle, this time with our b vector, where this is the 70 degrees. This is right in line with our y axis, the y value, and this is the x value, and this is our 5 meters. The sine of the 70 degrees is going to be, again, equal to the y over the 5 meters. So our y value is the 5 meters times that sine of 70. And I get something like 4.70, if I round up. And then the same thing with the x one. So we can kind of simplify and skip a few steps here, but the x is going to be equal then to the 5 meters times the cosine of that 70 degrees. So x is equal to 1.71 meters. So that tells me that this value here, my y value here, is going to be 4.7 meters up, and my x value here is 1.71 meters in the, across. Now, I can do a few things here with this in determining writing it in its vector form. But what I have to remember and what I have to pay attention to is it's important where my directions are. So this vector is still in the positive y direction, but I am no longer in the positive x direction. I'm now in the negative x direction. So why did I get a positive 1.71 instead of a negative 1.71? Because I would expect my x direction, the component, needs to be negative. When I write it in its component form or the unit vector notation, I need to write that that is negative. So I can either logically deduce it, or I could account for it by accounting for the proper angle from a unit circle perspective. The way to logically deduce this one is just to look at the direction of the vector. And this is actually easier in the sense of I have it drawn out, I see what it looks like. You might not always be given what the vectors look like on a graph. And you can always sketch them down by hand just to kind of get you a picture of it. But the fact that I'm going towards the west direction gives me an indicator. If it's north, it's positive y. If it's west, it's negative x. So that gives me the indicator that this needs to be negative. The other way to figure this out with less deduction, if that's not as obvious, is to take its true angle based on a unit circle. So if instead I calculated x equals the same 5 meters, and the cosine now, instead of being 70 degrees, needs to be 110 degrees, which is what we calculated it as down here if I were to take it from unit circle. If I were to plug this in, I would get negative 1.71 on my calculator. Now, we're not quite done with this vector because we also need to account for where it's starting at. So I didn't really need to account for this with vector A because its starting position is at the origin. And how do I know that? Given the problem, it doesn't tell me anything like I started at 0 meters. I can set the origin for this problem in particular. I can set the origin to be whatever I want it to be. In this case, I'm picking me. So I'm standing still, my friend is moving. I'm going to pick me as I'm 0 meters in the x and y direction. I'm the starting point. How far away is my friend from me? So the relative position for that, my A vector starts here at the origin, 0, 0. So when we write its vector notation form, I don't need to account for its origin because it doesn't really have a numerical value to it. It's 0. So I don't need to account for it because it is at the origin when it starts. I do, however, have to account for it for vector B because vector B is no longer starting at the origin. Vector B is starting at, and how can I figure out where vector B is starting? Well, if my friend is the one moving and he's in a constant, he's moving 4 meters, 25 degrees north of east, he stops, he turns, and then he moves 5 meters, 70 degrees north of west, then he has moved from this point, which I can calculate, I've actually already know, from my vector A. So this is 3.63 by 1.69. That's its starting point. So when I write my vector B out, I need to account for that its starting point is not 0. So I can continue writing vector B as, in this case, I have 4.70 meters in the x direction, plus, in this case, it's plus a negative, right? So plus a minus, so minus 1.71 in the j hat direction. And that's with reference. I can say something like from the point 3.63 comma 1.69. You can read my handwriting. But I put this in reference so that I know that this vector does not start from the origin. When I go to add it, I actually don't so much care about this origin point, or this point of origin for vector B, because I'm going to add it using a method of what's called tip to tail. But if they were to just simply ask, or if a teacher wanted you to find what is this vector in vector component form, you'd have to include that its origin point is not at 0, 0. So the other way I would write this in the component form is that it is 4.70 and negative 1.71. And again, I would just write the same thing. So from point 3.63 comma 1.69. And this is a sufficient way to represent vector B. Before we go about actually adding these, I'm going to fix, I noticed I made one mistake here where I actually, for my vector B, I just switched my x and my y values. So this negative 1.71, that's our x value. So this should be negative 1.71. And my y value should be positive 4.9. That would make a big difference when we start to go to add it. So always make sure that you're, 4.69. 4.7, not 4.9. Make sure that you're putting in the right variables in the right spot. So now, when we go to add these, you might have heard the term tip to tail. If you've ever heard that term, essentially what it means is I'm going to take the tip of the first vector, so this would be the red vector, and I'm going to attach the tail of the second vector to it, and I can kind of figure out the displacement between the two values there. And the displacement is the distance between you and your friend. That's actually what I want to find, and I can find that by adding these two vectors together. So when we go about doing tip to tail, we don't actually care about B's origin point if I put it in this component form. All I care about is directly adding it. So I can do that via the matrix component or the unit vector notation. Let's do the matrix component form first. So vector A plus vector B becomes the 3.63, 1.69. I'm going to add that to my vector B, which is negative 1.71 and 4.7, and I get some displacement, which I'm just going to call D for displacement, put a little arrow above it, because when we talk about displacement, that's a scalar. It's actually just a value, but I could figure out how far away my friend is and in what direction. So let's do both. But my displacement then becomes 1.92 in my x direction and 6.39 in my y direction. So that tells me the notation in the components essentially of this displacement vector. So in order to find its magnitude, I'm going to need to use Pythagorean's theorem. But before we do that, let's also write it in terms of the unit vector unit form, the notation. So I have vector A plus vector B, and I can write this then as 3.63 I hat plus 1.69 j hat plus, I'm going to write it on the next line because it's a little running out of space here, negative 1.71 I hat plus 4.7 j hat. And the way I do this addition is I only add like components. So I hat with I hat, j hat with j hat. So I can rewrite this then as the displacement, which is going to be equal to essentially 3.63 minus 1.71 if I'm just combining the terms. And those are both in terms of I hat, plus 1.69 plus 4.7 j hat, and that gives me the same exact value just in a different form. That the displacement vector is the 1.92 I hat plus 6.39 j hat. Now again, this is just giving us the displacement as the unit vector notation, right? Or the component form. How do I get this to be some kind of value? Like what does this exactly mean? Well, this means that this is essentially the two side lengths of a right triangle. So I can rewrite the displacement as its own right triangle. This is the displacement value, that hypotenuse. That's what I'm looking for. The I hat part is that's my x value. That's my x side. That's a value of 1.92. And then the opposite side of whatever this angle is here, which I can figure out in a minute, is 6.39. Now I can use my understanding of Pythagorean's theorem to figure out what this displacement is, right? So the actual value of the displacement is going to be equal to, so if you remember Pythagorean's theorem, a squared plus b squared equals c squared, where a and b are either of the sides and c is the hypotenuse. So that displacement is going to be the square root of a squared plus b squared, which is essentially this 1.92 squared plus 6.39 squared. And when I calculate that, I get, and again rounding to two significant figures, I get 6.67. So what does that mean? That means your friend, after being weird and walking away from you in very specific directions, is now a total of 6.67 meters away from you, from where you started. And we can use this to determine a lot of things when dealing with classic mechanics and Newtonian motion for modeling objects. And we can also go a step beyond this. Now, if this were like given to you as a homework problem, I understand maybe why you'd want to stop here and be done, right? But if I were curious about it and to say, well, by what direction did my friend really end up in relation to me, I can use this same concept of trig to deduce this. I can either use the new displacement I found, or I could even just use the tangent of the two sides, so the two components of that displacement vector. So in the way I would do this to figure out essentially what is this angle theta down here, I would say, all right, well, tangent is opposite over adjacent. So that tangent of whatever that angle is equal to that y value, which is 6.39, over the adjacent value, which is our x value, so it's 1.92. In order to solve this, I have to essentially get rid of this tangent. And the way I do that is I do arctan, or tan inverse. So tan inverse, and I can essentially, what I do to one side of the equation I have to do to the other, right? So this is a tan inverse, don't mind my drawing. But what this will do is this will get rid of the tangents, and it'll help me solve for theta. So essentially, I've gotten rid of the tangent on the one side, so the theta is equal to the tan inverse, or arctangent, of 6.39 over 1.92. If I plug that into my calculator, I get that angle is approximately 73.3 degrees. Now, that angle means this angle here inside the right triangle, this angle down here. So the way that the triangle is oriented, if I put it on a unit circle, that is still 73.3 degrees. So I could rewrite this displacement, although like if it were asking me, you know, what is the displacement vector, for example, because just displacement is a scalar. But if it were to ask me, like, you know, what is your displacement as a vector, I could write it back in polar coordinate form, as I could write it like this. I could write it. So we've written it already in the component form and the unit vector notation form. But I could write it back in the polar form by writing, well, it is 6.67 meters, and it is either at exactly 73.3 degrees, or if I wanted to use my, you know, kind of GPS kind of coordinate system, I can say, well, this is then east, so it would be north of east, because that's the direction I'm starting at, and I'm going in the north direction. And this is a really good example of how we use vector addition to figure out displacement problems.